Hi everyone, in this video we are going to prove the standard circle theorems. You might be asked at the GCSE to repeat this proof in a question, so you might want to carefully pay attention to the way we are actually proving these. To start, we need to remind ourselves our two basic properties that are going to be very useful. The first one is that if you take any 2 points here on a circle, let's say A and B, and you draw the two radii, then these two lengths here being equal, you've actually drawn an isosceles triangle. So if you then decide to draw the line that goes through and perpendicular to the chord AB here, what you're drawing is actually the perpendicular bisector of AB. So this is one important fact. The other one being that these two angles here are equal because AOB is obviously isosceles. One other important fact is that if you draw a radius like this and a tangent to this point here, the radius is going to be perpendicular to the tangent. So these two properties are now fresh in your minds. We can start proving the circle theorems. The first theorem states that the angle BAC, this one here, is half of the angle BOC, the angle there, or that the angle at the center here is twice the angle at the circumference. We say that these two angles are subtended by the arc BC. So to prove this property, we need to draw the radius AO, and as we've explained, we have two isosceles triangles. The first one is OAB, and the second one is OAC here, with the two red angles here being equal. So if you call this red angle Y and you call the blue one X, and if you use the fact that the three angles in a triangle add up to 180 degrees, you see that this angle here at the center has to be 180 degrees minus 2x, because we have x here and there. For a similar reason, this angle at the center here is going to be 180 degrees minus 2y. So this means that if you want to work out this angle here, you need to subtract these two angles that we've previously expressed in terms of x and y from 360. So if we go for 360 degrees minus 180 degree minus 2x minus the third angle, which is 180 degrees minus 2y, and you try and simplify this. So when you remove the brackets, you get 360 minus 180 plus 2x minus 180 plus 2y. You see that 360 minus 180 cancel out, and you're left with 2x plus 2y, which is twice x plus y, and x plus y is obviously the angle at the circumference we started with. So this is x plus y, this is twice x plus y. We are done proving the first circle theorem. Before we move on to the second theorem, it might be interesting to see what's going on if the triangle ABC here is actually an obtuse angle triangle, because you see this means that the chord AC here goes inside this angle BOC. Well, actually the proof is extremely similar, so the same result is holding. To prove it, again, we need to draw this radius here. And let's call this blue angle here X, and the red angle here, let's call it Y. So you see that we still have an isosceles triangle right here. So here we still have 180 degrees minus 2x, and we have another isosceles triangle right there. So the red angle here is 180 minus 2y. If we now want to work out the size of the angle at the center here, you see that we need to subtract the red angle from the blue one. So we get 180 degrees minus 2x minus 180 degrees minus 2y. Removing the brackets leads us to 180 minus 2x minus 180 plus 2y. The 1 80 cancel out, and we end up with 2y minus 2x, which is twice y minus x. And you can see that this angle here, y minus x, is the blue angle subtracted from the red one. So it's this blue angle subtracted from this red one. So it's actually the angle here at the circumference. And we've shown that this angle here, this one here, is twice the angle at the center. So the same result is still holding. Another important result is about the tangents at 2 points A and B that are on the circumference of a circle. So if we draw these two tangents, here they are. Remember that we have two right angles like this. And we need to prove that this length here is exactly the same as the length there. So let's call the intersection point here C, and let's draw the line segment OC. So what can we see? Well, we see that the two red lengths here are equal because they are two radii of the same circle, that the hypotenuse in these two right angle triangle is the same side, and that we have two right angles here and there. This means that for the two triangles OCA and OCB, we can use the congruence theorem. They have a right angle, the hypotenuse is the same, and they have another side in common. So the RHS case from the congruence theorem actually allows you to state that these two triangles are congruent. And the fact that they are congruent obviously means that the third side here is going to be the same length. So this is how you prove that AC is equal to BC. So basically here you end up with a kite. By the way, saying that these two triangles are congruent, you've also proved that this angle here is the same as this one, and that the angle here is the same as that one. From the first circle theorems, three more properties are very easy to derive. The first one is about angles in a semicircle, just like that. So you see that here we have a full semicircle right there, and so you can apply the circle theorem to say that this angle here is half of this angle. So because here we have an angle on the line, we have 180 degrees, this shows that the angle here is 90 degrees. So we have a right angle triangle when one side here is a diameter of the circumscribed circle. The second property is about angles at the circumference subtended by the same arc. So here are two such angles. So you see that these two angles here are subtended by the same arc there. And so these two angles will always be equal. It's quite easy to see if you actually draw the angle at the center subtended by the same arc right there. You see that these two angles, using the circle theorem, can be shown to be half of the angle at the center. And you can check that this is valid for any angle that you will draw subtended by the same arc here. Actually, all these angles here are all equal because they are all equal to half of this angle at the center. The third property is about cyclic quadrilaterals. So this means that we're looking at quadrilaterals that have all four vertices in the same circle. And you can derive a very interesting property about opposite angles in such a quadrilateral. We'll see that these two angles here are equal to 180 degrees together. To show this, we can just draw these two radii, and then it's easy to show that this angle here is half of this one, right here, and the angle there is half of that one, there. You see that these two angles here and there, they add up to 360 degrees. So if you add up half of these two angles, it will add up to half of 360 degrees, that is to say 180. So you've shown that this angle and this angle add up to 180. The same reasoning can be followed to prove that the sum of this angle here and this angle there is also 180 degrees. one last and more complex property is called the alternate segment theorem. In this theorem, you're considering again one angle at the circumference, and you're comparing this angle here at the circumference with the angle made by the chord joining the other two vertices and the tangent here. And so you can say that the angle here between the tangent and the chord is equal to this angle right there. To prove this property, we are going to use once again the circle theorem. So let's draw the two radii here that we need to show the angle at the center. So we can say that if we call this angle x right here, this one is 2 times x, because this is the corresponding angle at the center. Now, if we work in this triangle here, because it's made of two radii, we have an isosceles triangle, and we can work out one such angle. So we can subtract from 180 2x, and we get the sum of the two angles here at the base, and divide this by 2. We get 90 degrees minus x for this angle right here and for this angle right there. Okay, now you need to remember that this radius here is perpendicular to the tangent. So we have a 90-degree angle right here. Okay, so now look at this. The whole thing is 90 degrees. This thing here is 90 minus x. So if you want to work out what remains here on the inside, you are going to subtract from 90 degrees this 90 minus x, and you will get 90 minus 90 plus x. These two cancelling out, you're left with x. So you've proved that the angle here in between this chord and the tangent is equal to the angle at the circumference right there.